My name is Jayrold Bautista, and together with me is Valérie. I'm based in Singapore. Valérie is based in Belgium, so she's doing this now, right, from Brussels, Belgium, and we are from Dow. And I think some of you may be familiar with our company, and we are mostly involved in your silicone structural glazing and your weather seals for your facade. So today we'll be talking about safety of silicone bonded facades, and I think we will be actually focusing on seismic performance of silicone bonded facades. And I think earthquakes. This is probably one of the most terrifying event that one can have. One of the most terrifying. One of the usually it will it happens very sudden, and I have my own fair share of experience when it comes to earthquakes, so I should know. Back in 1990, I experienced one of the strongest, if not the strongest, earthquake in the Philippines. It was magnitude 7.7, and it was 45 seconds of just violent shaking. And I will never forget that day. And it was just really a very terrifying event. Many buildings collapsed, bridges destroyed, and unfortunately many fatalities as well. I think some of you, it's in one way or another, being in Indonesia, have experienced it as well. I mean, just looking at these charts here, countries with the most earthquake, Indonesia is at second, and even just the location of Indonesia itself. Looking at all of these dots here, just the number of earthquakes that Indonesia experienced from 1900 to 2019, and looking at the magnitude is just there's just really a lot. So if you look at, let's say, some of the metropolitan areas, LA, Tokyo, Shanghai, Jakarta, these are all metropolitan areas that are part of seismic regions. And truly, in the past few years, in modern times, there has been lesser and lesser building collapse, like major building collapse, especially in the urban areas, right? But still, we have to look at some of the components of the building, just the main, not just the main structural components, but also the non-structural components, just like the facades, because they can also have some damage during some earthquakes, just like what you can see in the slide right now, wherein you can have some visibility damage on your facade. You're talking about gasket dislodging. You're talking about maybe glass dislodging as well. You have glass breakage or glass cracking, and sometimes maybe even some glass falling from the facade itself. So these are some of the things that you should be looking at as well, and not just the main components of your facade, or of your building, I'm sorry. Now, if you look at the seismic design of the building, I mean, the weight of a structure that you are designing for seismic is directly proportional to the seismic loading that it's going to have. Building structures are heavy, and the response is influenced by complex vibrations. And let's just say a lot of the main structures right now are concrete, and concrete is not really a very good material for seismic design. So what you'll do is typically you'll go to technology, you'll go to let's say some dampers to make sure that seismic loads are better managed. Now, if you look at glass facade relatively to the main structure, it is lightweight, and it is influenced by the building's main structure when it comes to seismic loads. The seismic loads you'll have the in-plane loading, and also you'll have the out-of-plane lateral loads. Now, these loads are coming from the P waves from the earthquake, which makes buildings go up and down or shake up and down. And earthquakes will also have their secondary wave, or S wave, which makes buildings sway from side to side. So you can just imagine these waves and how they're going to interact with your main structure and how they're going to affect your facade. Now, the main idea about seismic design for buildings is that you should isolate the facade from the main structure. So for example, how would you do that? You'll have you will design your facade joints to be able to accommodate those movements or to allow movements when there's a seismic load. And then also, of course, your connections. You're going to have some slippage on your connection to ensure that there is that isolation of your facade to the main structure. Now, the other thing, of course, is that you put those theory into test. So it's also very good that you would put or test your facade under those expected maximum movements so that you'll be able to mitigate those assumed loads that you have regarding seismic. We can look at the design codes, and Valerie can talk about the design loads for the United States and also for Europe.
Yes, indeed, Jayrold. So there are different building codes that can consider seismic action. In the US, we have two such important documents. It's an area prone to earthquakes. We have the American Society of Civil Engineers standard that calculates the horizontal force on the non-structural component and assesses the glass fallout seismic drift, so the displacement that needs to be larger than a certain limit. Then we have also the AMA, so the American Architectural Manufacturer Association standard, the 501.6. It's an often used testing standard that we use a lot within Dow. It's characterized by the excitation type on the bottom left of your screen. So you see it's a monotonically increasing amplitude, sinusoidal drift cycle, and it determines the serviceability and the ultimate drift limit for the glass. The way it's tested is based on a worst case scenario. So you're going in your mock-up to choose the largest glass, the thinnest glass, the most fragile one, the smallest clearances, largest drift index, and so on. And then with this test, you can assess different key design elements of the curtain wall system, such as the SG joints, so the structural glazing joints, the drift, and of course, the primary objective is to determine if we have a glass fallout limit that is within the tolerated value. In Europe, we have the Eurocode 1998, the part 1, that evaluates possible hazard for non-structural elements such as curtain wall. It's a simplified method for a static horizontal force. And then we have the curtain walling standard EN 13830 with Annex D as well. That relates to the seismic resistance, where you can do the testing as well and assess on top of it functionality of the facade in terms of air and water tightness after the seismic event.
Right, and now going more towards Asia, so some of the more popular ones, we have JASS 14, which is from Japan, and this talks about, it's for curtain wall itself, and this one talks about levels of deformation on the facade itself, depending on the strength of the earthquake. And then if you look at more locally here in ASEAN, for Indonesia, we have SNI 03-1726, and this is I think the latest version is the 2019 version, and a lot of this loading is based on ASCE 7 as well. We look at the different systems used for glazing. One of them, of course, is captive systems. Now, the more inflexible our facade system is, the more potential it is for damage due to seismic loading. So damage typically happens when there is incompatibility between movements of your building versus to the movement capabilities of your facade. So for example, if you don't have enough joint widths to accommodate those movements, if you do not have enough slippage, as I mentioned a while ago, right, in your brackets, in your facade itself, it's gonna have some, it's gonna cause some problems for your facade. So if you look at, let's just say glass, the glass itself, looking more into that, if you have framing members and you have a system that is rigid, your glass is very prone to touch or from the impact of the framing systems on the edge. And because of that, you may have some glass cracking, or even worse, you may have some glass breakage as well. So if you look at this, all of this loading, so you have your out of plane loading, you have your in plane lateral loads for your facade, and truly one of the good things about modern times. Now there's a lot of buildings that use unitized curtain walls, and unitized curtain walls are very good when it comes to accommodating, of course, provided that they are designed properly. If you look at unitized curtain walls, the P waves of an earthquake, so that movement, that up and down shaking from that earthquake, actually that's taken care of by the stack joint in your unitized curtain walls. Your out of plane loading is taken care of by your rotation in the mullion area, in the brackets of your curtain wall. Now what you're left with is the S wave, which is the side-by-side shaking. Now that is taken care of by your connection to your glass. So it's either you have a captive system, which is what we're showing right now, wherein you only have this aluminum capture taking care of holding the glass in place, or you will have a structurally glazed panel wherein structural sealants are used to stick the glass to the frame. And between these two, the structural glazing will outperform your captive systems. So as Valerie will show on the next slide.
Yeah, indeed, silicone structural glazing or bonding offers you a very interesting movement accommodation capacity that can really contribute to improve the performance of a curtain wall that is exposed to a seismic activity. And that can be related to the structure itself of the silicone. As you can see on the left of the screen, on the bottom left, you have the shape of the polymer, which is really a twisting helicoid. So it already has some flexibility. And then the angle between the bonds, the SIO bonds, is also quite large. And both of these features already contribute at the start to a good movement capacity, and is also a reason why we use successfully silicone for weatherproofing, but also why it will, opposed to other polymers, have a better capacity to accommodate those larger seismic movements. So we have extra flexibility in the glazing parameter. We can reduce the stress concentration in the glazing and really distribute the stress more homogeneously. Another benefit is that our modulus in shear is typically less than in tension. So it means that you are going to accumulate less stress in those shear deformations than in tension, which is also a benefit. On the top right of your screen, you can see the Washington Mutual Tower in Seattle in the US, which was built in 1987. Now, Seattle is not the most favorable climatic condition. There's a lot of rainfall. There's also a lot of temperature swings. And on top of it, combined with heavy winds and also regularly seismic activity. Now, this building, for example, got a seismic event in 2001 of magnitude 7 on the Richter scale. And despite all these adverse conditions, we never got any report of failure of this building that has two-sided structurally glazed insulating glass units.
Yeah, and at the bottom, you'll see this, well, this is a building in Jakarta. You probably are very familiar with this. This is the World Trade Center building and completed in 2017. It's a four-sided structurally glazed curtain wall panel. And this, since 2017, has experienced earthquakes in Jakarta, or at least near Jakarta, that is magnitude 5.0 or higher. And so far, and of course, we're always crossing our fingers that we haven't received any report of let's say silicone damage because of seismic activities for this particular building as well.
Understanding of the seismic performance of our silicone structurally glazing and our efforts to expand our knowledge date back from quite a long time. So we started evaluating that back in 1996. Where we were evaluating small test pieces, H pieces, TA joints, and also did quite some post-seismic building inspection. And based on this early evaluation, we defined a design stress of 0.35 megapascal, 50 PSI for specific Dow silicones, and also a 25% design strain for some products. To further understand the seismic behavior, we expanded experimental testing in 2012, and that was really related to a real project. You can see in very small characters the reference study that you can consult on the internet. So here again, we combined small-scale experimental observation and then larger testing according to the EMAS standards. We have here a four-sided structurally glazed curtain wall unit, and it was a unitized system. Now, unitized system, as Jayrold already explained, consists of a system that is normally structurally discontinuous from level to level. It's decoupled from movement in the adjacent floors. But in this project, we decided to look at a worst case scenario. Thus, we assume that the unitized system would not behave as intended in sway, with panels that slide in plane at the horizontal stack joint and keep a rectangular shape, but that there would be some malfunctioning and that we would have a stick-built system with the glazing frame that is continuous over multiple stories, and so that we have a racking under in-plane story drift, meaning also that under this in-plane lateral load at the top of the panel, we are going to see that deformation in the shape of a parallelogram. Logically, this racking is going to transfer larger strains to the structural sealants, but that would show that we have that we would also fulfill in the normal utilization in the sway mode. So here on this video, you can see more details. We have the sway condition, we have the racking condition. The sway was less severe as anticipated. We confirmed that the allowable design limit for movement capacity was good. We only observed damage to the sealant after the glass fallout limit was reached. And for unitized system that would work correctly, we do not anticipate any damage tearing at this target drift. Now, how do we perform any evaluation of a project that needs to comply with seismic performance? We'll start first with dimensioning our joints for wind loading, assuming normal. Can you go back to the before Jayrold? Assuming normal 20 psi or 0.14 megapascal, and then we need to ensure it can take all the deformations that are anticipated for seismic performance. And that is data that we are not calculating. It's provided by our customers. So they will design facades for the seismic movement, and then we will look at being able to accommodate that movement. Now, on the next slide, we can see how we are further expanding our knowledge today, because you can imagine that this type of large-scale testing mock-ups is time-consuming, it's expensive, it does not allow you to evaluate all the possible configurations. For example, doing a parametric analysis to understand the influence of the joint dimensions, the aspect ratio, and other parameters, it's just impossible. And in the meantime, since 2010, we have seen a lot of progress in terms of finite element analysis and use of this to better understand the limits of our material. We have been using that successfully in other applications. We are looking at cold banding, at bomb blast, and we are also now applying this for seismic performance. So the idea is, again, that we build some small-scale experimental test results. We build a hyperelastic accurate material model with the proper meshing. We validate that we can predict what we see experimentally on a small scale, and then we repeat that exercise with one large scale. And once the model is validated, then we can run all the parametric analysis that we want. So what we have seen in the first validation of the large scale here of the EMA test is that we think that the tearing is going to occur when the strain reaches a certain ultimate value in the joint, and that fallout will occur when the tensile or shear stress reaches also a strength limit. This is a preliminary result because we have in this specific case a joint that has an L shape, and this is not the most common. So we are currently building more large-scale experimental tests with a rectangular joint of a few dimensions. We are going to model that, and once this is done, then we'll get to really a full parametric analysis. So we are also working together with Marie Curie individual fellowship research projects, together with leading technical universities in facade and in seismic design. So we have the Dutch University of Delft, and we have the Italian University of the Sapienza in Rome, as well together with the well-known facade contractor Permastilisa. So it's a project duration of 2 years. It's going to end by July 2023. It's led by Dr. Simona Bianchi, and the project is following a similar approach. So we have a lot of mock-ups that are going to be experimentally assessed, not only on the base of seismic performance, and repeated seismic performance, but also assessing what we mentioned in the beginning of watertightness, airtightness, so really the functionality after a seismic event. And that will then be gradually increased until we reach failure for the different systems. They are going to change details of the system, for example, the stack joint, but also of the joint dimensions. So we have really a maximum of experimental results that will then be modeled with finite element analysis again, so that we understand all the different parameters. And again, there will be, of course, a big attention dedicated to understanding how the damage is occurring in our silicone joint, but also in the elements of the system.
Thanks, Valerie. And now we go to some of the case studies and for seismic performance of some of the real or actual projects that we have. So for example, this building, I think this is very familiar for a lot of us. I haven't been there. I hope to one day. But this is the Apple Park, or the Apple headquarters in Cupertino, California. And we're looking here at the sliding doors, and these sliding doors are, you have 7 meters tall by 28 meters wide doors and a total of 180 tons. And this project or structure being in California, it's very important that these are tests for seismic performance. Now, these doors, as you can see, they're huge and they're really heavy. So it's very difficult to do the test like what's Valerie has shown a while ago. So of course, we can do some FEA, but then they have decided that the team that was doing this have decided that they want to do a mock-up, a smaller version, but still will be able to simulate that movement that the sealant joint will have when they're in the event of a seismic, in the event of an earthquake. So right now, you can see we're using here one of our products, 993 structural glazing sealant. It's a 2-part structural glazing sealant. So what they did, you can see there's the glass there. They keep on putting loads there, and then this joint, as you can see, just keeps on deforming, of course, because of that loading. This joint actually is around, I think, double checks 24 by 30, if I'm not mistaken, 24 by 30. That's the dimension of that joint. So as you can see, what happened here was they keep on adding loads to this, of course, to simulate that low seismic loading on this glass and on that joint, and the glass break even before the sealant actually failed or broke. So that, as again, you can see that the sealant was able to accommodate those movements coming from the seismic load based on this particular mock-up. Then we go to, again, another very, I think, prominent project, which is the Steve Jobs Theater, also in the same area. So this project, as you may know, right, the concepts that full clarity as much as possible. There's no column, there's no mullion, very lightweight looking. So all you have is this glass and this carbon fiber roof that you have at the top. So they wanted to do a seismic performance test here on that door. So as you can see the swaying from here, and then so you can see how extreme that movement is from that particular video. And in all of this extreme deformations or extreme conditions that you can see here, the sealant was able to handle all of those movement from that swaying. Now, one thing we would like to emphasize here is that here we are showing to you a detail of the glass wall here. And as you can see from here that there's no column, there's no mullion. So everything, the sprinklers, anything that has to usually go in those areas actually went inside this joint here, as you can see from here. So this was, you can see there are 4 layers of glass here. And the idea here is that this was possible. This is not a very usual design. As you can imagine, the key thing here is that during the project, they engaged us early. and that engagement allow us to agree on design, to be able to test those design, and to be able to come up with the architect's vision on this particular project. So key thing there is that if you have those designs that are unusual, you can engage with us early, and we'll be happy to discuss, those designs with you.
So I hope this presentation has given you some insights, useful insights in the contribution of silicone structurally glazed facades in seismic performance, and that the way we are behaving is really a big advantage for this application. So as Jayrold said, we are really very keen to collaborate for successful facade design. It's really important that you engage whenever you have challenging projects early on, so that we can optimize really the performance of our materials and make sure that our buildings will remain standing tall despite this type of events. So we'd like to thank you for your attention and welcome any questions.